So go yell for those guys. Where did they go? Come on, hurry up. Where you at?
Yes,
4, 5, 6, 7. Okay, we got everybody. So we need you for intros.
We're almost there.
Well, we should wait for everyone to populate the webinar.
I'm keeping track. We are at right at 120 people.
So if I just
far.
stand here, I'm good, right?
We'll get everyone into the big lecture hall here first, and then we'll get going.
So whenever you guys think I look photogenic enough to get this off the ground. Yeah, I know, but.
Yeah, there you go.
So good afternoon or good evening, depending upon which coast you are at right now. This is the Demos Unleashed AAPT demo show. It also functions as our University of Iowa departmental demo show. And so there's a lot of non-AAPT members also attending this session. What I have here is the people who are with me and going to help out our demo people from across the country. I have Paul Nord here from Valparaiso University. I have Sam Sampere from Syracuse University. I have Cliff Bettis from University of Nebraska at Lincoln. Back behind us, we have Dave Maiullo from Rutgers University. And if we swing back and show the man behind the camera, this is David Sturm from the University of Maine. And then the other man behind the camera is Daniel Davis from Harvard. Okay, so we have quite a few demo people helping us out here today. My name is Dale Stille. I'm from the University of Iowa. And since I'm the host institution, all of these demos pretty much, except for a few, are a part of our demo collection that we have here. Okay, so with no further ado, we will start with our first demonstration. Might have to touch them.
Concentrate, everyone, concentrate. While we're waiting, do you want to explain what PIRA is?
I would let you do that.
Okay, so the letters on this barrel, PIRA, stands for the Physics Instructional Resource Association, and we are a subgroup of AAPT. Anyone can join PIRA. We're interested in demonstrations, apparatus, how to use this stuff to teach physics. So if you have any of those like interests, please join our little group. We're still waiting for the yellow A. Do people know what's going on? People probably don't know what's going on. We have 4 vacuum pumps. Each vacuum pump was at some point connected to these steel drums, 55-gallon steel drums. The vacuum pumps were removing the air from the barrels. Outside air pressure was pushing in on the barrels. Air pressure inside was kind of pushing out, but as the air left, it was pushing out less and less and less until outside air pressure collapsed the drums and we hear the bangs. Okay, excellent.
So
Nothing like a big drum, right? Well, yeah, I mean, you know, it's a demo show, so we're going to show some things that most people probably can't quite do in their classroom all the time. And this next demonstration is actually one of those. In fact, what I have right here is basically a 1 watt green laser pointer. These are hard to find and hard to get, and are actually something you probably shouldn't have in your classroom at all. At the same time, we would like to show you, just having that green laser on the screen there, it's actually quite powerful. And you can even see it fluoresce a little bit from all the dust that was shaken from the ceiling when those drums actually imploded. So we actually have quite a big bright dot there on the screen, and that's a lot of energy. And that, you know, that's that green wavelength, and it's quite bright there too. And we're actually most sensitive to green light than any other wavelength of light as human beings, most of us anyway. But here we have a purple, and this is a 1.5 watt UV laser pointer, something no one should actually own unless you're completely insane like me. So this is very bright on that screen, and you can see it even fluoresce a little better from the dust that's coming from our ceiling. And let's actually show very easily just how hot these lasers are. So here I have a normal everyday balloon, black balloon. If I go ahead and use that, should actually, well, it looks like it's not going to actually bust through that sky. So what do? Well, I want to increase the energy, right? So how do you increase the energy of light? Well, you go and you use a wavelength that's actually just like that. And it just popped that balloon very quickly. Let's see if it can pop a green one. I'm actually quite curious about this. I haven't tried this before. Oh yeah. Let's see if we can pop this one right here. Let's see what happens here. Oh, it even popped the one that had helium in it. I wanted something to float away. Let's see if we can pop a yellow. Yep. And let's see. It's purple, but hey, it won't do the purple. It's kind of neat how it fluoresces, actually. So there's one it can't go. But let's see if we can do the orange. Yeah, so it did each one of those instantly, except for the purple. And why not? What's happening there? I don't know. Does anybody know why it doesn't pop the purple?
Purple is really strong.
Purple's really strong. Thanks, Sam. Well, the color that's coming out from this is, Paul, purple. So it's actually just sending it back out, right? That's that purple, right? That's what we got there. So don't use these in the classroom, but they are awful lot of fun for a demonstration show. Our next demonstration is
I'm not going to tell you the name of this demonstration because it'll give away the secret or give away the ending. So in this dewar, I have liquid nitrogen. It's really air that is so cold that it is turned into a liquid. So air that's so cold, it's turned into a liquid. And I'm filling up this little glass jar with liquid air, liquid nitrogen, whatever you want to call it. Get rid of these little puddles down here. I'm going to cover this with a glass bell jar, get rid of the bubbles of nitrogen around the gasket. Now I'm going to cover this with a safety plastic protective shield. And now I'm going to open up a vacuum pump. So same kind of vacuum, exact same vacuum pump that was removing the air from those steel drums. We're going to remove the air from this glass chamber. And it's actually quite surprising that the glass chamber is going to hold up better to outside atmospheric pressure pushing on this than the steel drums did. And so I'm removing the air so there's less air pounding down on the surface of that liquid air. So you can see it's boiling away at a faster rate. I'm going to keep opening the vacuum pump. making that boil away. What does that mean, boiling away? Well, the molecules that are in that liquid, the hottest ones are leaving that liquid. Well, if I'm getting rid of the hottest ones, whoa, I leave the coldest ones. And if I keep making a liquid colder, you know what happens? It turns into a solid. So right now, what you're seeing inside that vacuum chamber is solid air, air that is so cold that it's turned into a solid. I know what you're saying. Let's pick it up. Well, let's think about this. Liquid air is about 300 degrees below 0 Fahrenheit. I still want to pick it up. Let's do it. So what I'm going to do is close the valve. I'll open up this valve. Oh, whoa. That was too fast. Well, yeah, now we're done with it. You saw what happened though. That immediately turned into a liquid. I could play that game all day long. I'd never. You want to play it again? Okay. Dale said, play it again, Sam. No, play it again, Sam. Okay, so we're going to fill this up again with some liquid air. Cover me up, close the valve, please. We'll open up the vacuum. And you can see that the more I open the vacuum, the faster and faster that evaporates. Now it stops boiling. Well, let me open it again. We're removing some of that atmosphere that's pounding down on the surface. I can evaporate even faster. It's getting colder and colder as I remove the hottest molecules in there. And pretty soon I get so cold that what remains turns into a solid. And there it is. Oh, turning back into a liquid. There again, solid air, air that is so cold, it has turned into a solid. And now let's get some of it out. I'll close that, crack that open. Oh, it immediately turns back into a liquid. And if I open up the vacuum, it goes right back to a solid. So solid air. Not many people on this planet have seen solid air.
Speaking of air, the thing that surprised Sam there was when his vacuum chamber let a whole bunch of air in very quickly and it knocked over his dish. We have another one to do that. I have a pipe here connected to another vacuum pump. I'm going to suck all the air out of it and let it back in really quickly. Before I do that, I'm going to put a ping pong ball in there. So let's get that ping pong ball down to the other side. Is this going to work? I'm going to blow it down. The valve is open. Uh-oh.
We got it.
Oh, you got it disconnected. Okay. Got to load it. Well, all the way at the other end. We are going to seal that with some Mylar foil. This is thin film. You buy this as an emergency blanket, very lightweight. You can pack it with you anyway. Put it on here. There's a gasket, and we're just going to seal that on. And there's another gasket at the other end. This is enough to hold back the air pressure, which is 15 pounds per square inch. But and there's one at the other end. We're going to rupture that one at the other end. The air is going to rush in. It's going to drag that ping pong ball along with it. Let's make sure we're nicely aimed at this series of, what are you drinking, Dale? Mountain Dew? Mountain Dew is the local beverage of choice. All right. For me doing this, it makes quite a loud pop. The rest of you can cover your ears, but I need to wear these because I need one hand free to pop the thing.
Don't shut the valve until after you pop the panel.
Okay. How much did you let it go down, Dale? All right, ready for a countdown? Got our ears covered? 3, 2, 1. All right, how'd the ping pong ball do? 3.5.
There we are.
That is
So-
just the power in the air. Where was the energy stored when we were doing that? The energy was stored in the room. We took everything out of the tube.
3.5
And the remains of a ping pong ball.
And if anybody was here watching us in our actual audience, I'd give this away to them, but that's the way life is. Sam, you're going to explain this one? The gravitational waves.
Here we have a rubbery fabric, much like the fabric of space-time. Right here, I have two black holes. And they're on a drill, so I can spin them around, and I can spin them around at very different rates. So you know what happens? You've heard, it's been in the news. Black holes have been observed by LIGO, the Gravitational Wave Observatory. It's an amazing science experiment. So black holes are rotating, and as they rotate around each other, they move faster and faster and faster. Their frequency increases. And as they do that, gravitational waves are sent out through all the universe. And we can detect them here on Earth with the LIGO Observatory. And you should be able to see the waves strobing with the camera that we're using to project this video. And you should be able to see those waves travel across the fabric of space-time. So astronomers detect these waves, they detect the frequency, the change in frequency, and they can determine the mass of the black holes and how far away they are from us.
Beautiful. Here, Sam, I'll take that. So that we used a spandex sheet, rather large, and we used a drill to do a cosmology experiment. But you know, you can use apparatus that really isn't even that extravagant to do a whole nother experiment, including cosmology, and that would be this right here. What is this right here? Well, this is a garbage can. And I need my assistant, Sam. And if you were here right now, I could do this. And you probably wouldn't notice anything unless I was doing it right at you, that something's happening. You know, in science, excellent. You really need some evidence of things, right? We like evidence in science. We like to do experiments, but basically we're looking for things to happen. So to prove to you that something's happening, every time I hit the end of this garbage can, Sam's going to stand out there with that candle.
I have a better idea. Why don't we come back to that after our fog machines are heated up?
Oh, that would help a lot.
Right?
Yeah.
Let's do that. So while we're waiting for fog machines to heat up, let's talk about some apparatus over here. Okay, over here I have a thick slab of copper and a very, very strong magnet. Magnets do not stick to copper. They just don't stick to copper. However, if I take this magnet and move it near the copper, I feel a force that's resisting my movement. So if it's sitting here doing nothing, not a big deal. But if I try and shove it fast across the copper, you saw the copper sheet move, and that's not because I'm moving it. There's a force that's pulling this that's not me touching it. Okay, something else that's really cool is if I take this and drop it, it just makes a soft touchdown versus landing on a tabletop. Soft touchdown. And then something else that's really kind of fun. I like this one too. It tips over. And again, it doesn't go. Oh, there's steel under this table. It doesn't go bonk. It goes soft. Okay. We're going to change some material properties of this copper by plunging it in liquid nitrogen. So we're going to take this copper plunge it in liquid nitrogen, and let this copper come down to liquid nitrogen temperature. And that's going to take about 5 or 10 minutes or so. So we're going to come back and revisit this demo after this copper is cold. So while we're waiting for that, let's move on to yet another demo. So we're going to head on over across the stage to Dale.
So we actually have two versions of glass breakers here at the University of Iowa. The first version is we have the high frequency glass breaker. This is going to be at, for this particular glass, is somewhere around 893 hertz. And what's going to happen is we're going to drive it with this speaker horn that you see in the back, the little round knob there. On my side, it looks more like this as the driver, but it's just basically a very robust speaker. And what we're going to do is we're going to drive this beaker with the same frequency that emits if you were to touch the glass like this. If you went like this, the sound you hear is what you play back at it to send it into resonance. All right. And when it resonates, you can, if you are able to see it with a strobe light, which we can't do with the camera, but it looks like the beaker is going like this right before it breaks. Okay. And so the whole glass, you think of glass as a solid, but it actually bends pretty well, especially in environments like this. And so what we're going to do is we're going to send that same sound back at this glass. And you can see that it only survives a certain amount of amplitude before it completely shatters because it's trying to bend beyond the elastic limit of the glass. All right.
So we'll go back to this one. Thank you, Dale. May I grab your microphone, please? You may. Thank you. All right. And moving right along and right back to where we were before, we now have some fog, which we'll use in a little bit. But first, we're going to have Sam step out there with that candle in his hand. And again, Cliff doesn't know anything's happening with this demo unless I do that to him. But you can't actually tell what happened to Cliff. So here's some evidence. Sam is holding that candle out there. And I should. Oh, I can't quite do it. See, Dale's vortex cannon isn't quite good as mine. Wait, I know what to do. Get closer. So you can see that there is something happening because we blew out a candle with this device. And that's actually what it's really all about. You want some evidence of things. But the best way to do science, the best way to do physics, the best way to do anything is to see what's happening. So let's see what's happening. And for that, we're going to use some theatrical fog. We're going to fill this garbage can with some theatrical fog. And for this, I'm now going to take this and hit the end. And now you're going to see what was happening every single time I hit the end of that vortex cannon, because those rings were actually happening every single time. We couldn't see them before because there was nothing to trace out that path of the air, but that's happening every single time you hit the end of this garbage can. Oh, let's see if I can hit it this time. Give me a target. Oh, excellent. Thank you, Sam. See, I'm not that bad. So, yeah, and that's a round hole we have here in our garbage can. And so you say, well, yeah, Dave, you know, a smoke ring is going to come out of there. And that makes sense, right? We all agree with that. But, you know, Dale has actually given us a square. So what we're going to do now is going to take the square, we're going to put it on the end of our garbage can. And I'd like you all to ask yourselves, what's going to happen now? What will we see coming from this garbage can? Oh, what do we got to do? We got to do the experiment. That's how we really learn in life. That's how we know anything at all. So let's do the experiment. Thank you, Sam, man on the spot. Let's see what we get from our garbage can now. and it's still a smoke ring. Yes, David, you're waving. Thank you, David. It's still a smoke ring. So that's kind of neat. But remember, do it again. Oh, up there in front. Right there. Thank you, Dale. Perfect. Got it. Thank you, Sam. Just like that. Look at that. And what's more fun than a garbage can filled with smoke? Well, we can actually do, just like with that spandex sheet and just a normal drill and a couple casters, we can actually do cosmology. You know, the whole LIGO idea, the whole idea that we have gravitational waves is a rather recent one in science and cosmology. And it's actually very exciting. And it's wonderful stuff. And it's a lot of things there to explain and understand. But you can actually see what these gravitational waves look like with the same device. Because what we now have put on the end of this device, we're getting some fog? Ah, that's okay. We got enough. That's good. Thank you. The foggers are notorious for being really bad. So what we have now is an ellipse on the end of our garbage can. And if I do this, you'll see there's now a smoke ring. Oh, that's actually shaking as the ellipse moves through. Let's see, did I get it in the right spot? Thank you, Dale. Let's do it again. And that quadrupole motion is exactly what those gravitational waves, how they oscillate across our universe when those two big black holes combine, or actually, everything actually is giving out gravitational waves. We can only see the one so far from, you know, these larger collisions. Maybe sooner or later, we'll actually be able to observe it, I don't know, when two smaller bodies collide. But that's doing cosmology with a garbage can. Hey, what's better than that? There you go. So what is next? Is you want to break that other beaker?
Time for question?
Do we have time for a question? Sure.
All right. Janice has a question.
Yes.
You want to take that?
Sure.
All right. And David, can you hear Janice? Or do you have a quick question in the chat? Keep going. Keep going.
So we can't, I guess we can't hear the question if we figure out how to hear it.
We can see things in the chat.
Okay.
If you type in the chat, we can work with that.
Okay.
We just don't have enough control.
Okay. So the questions can go into the chat, right? That's how we can see questions so that we can answer them here live for you. So go ahead and put that question in the chat and we'll try to answer that. Anyone? I think you're ready. Now it's cold. We're good? All right, Sam, you want to do that one next, or are we going to do this one next?
Okay, we're gonna do the glowing one.
The glowing one. I love the glowing one. We're turning off the lights too, right?
Yes, we can. So this is the second of the two glass breakers we have. This one is very low frequency. The glass we're using is just a plate of glass that looks like this that I put some fluorescent paint onto. We set it over a system of speakers so that when these two speakers push out, there's a hole here and a hole back over here that the air pushes upward. When the speakers come this way, there's a hole in the center that pushes the air up out of the center. So basically what we're going to do is bend that piece of glass like this. And I have some black lights here so that this is black light sensitive. With the camera, you're going to see some really unique strobing effects when this starts to reach resonant frequencies. What did? All right, give me a second. Oh, I see. Somebody was playing with my stuff again. Here we go. All right, so if you notice right now at the ends are oscillating up and down. The middle part is also oscillating up and down, but on the nodes here, those are completely quiet. So there's no oscillations at these 2 points right here, only oscillations at the outside and in the middle. And as we keep turning up the amplitude on our speakers, driving this plate harder and harder, and eventually we go beyond the elastic limit of a pane of glass. And you can see these break a lot cleaner. They all usually break in the center in 3 pieces. All right, now Sam can come back to his cold copper plate.
So a few moments ago, you probably heard some violent boiling coming out of here, and that was the copper plate finally reaching liquid nitrogen temperature. So I'm going to take this out, set it on the table, and we're going to play those same games with the magnet that we played before. So I'm going to take this magnet and watch how much slower it drops to the copper plate. Watch this, I'll drop it from even higher up. It bounces before it comes to a gentle landing on the plate. If I set it on edge like I did before and tip it over, that is just so cool.
So how did we amplify that effect, Sam?
We amplified that effect by cooling the copper down. When the copper cools down, its conductivity increases by an order of magnitude. When I change the magnetic field near the copper by bringing the magnet nearby, currents swirl in that copper to oppose that change in magnetic field. And you know what happens when you bring opposing magnetic fields together? They repel each other. That's the nutshell of how this happens. We'll explore this a little deeper in a demo in a few minutes.
Sam, there was a question from the audience. What would happen if you put the magnet in liquid nitrogen and cooled it?
Okay, so the question is, what would happen if I cooled the magnet? The answer is, I would not change the magnetic field of this magnet by cooling it. So cooling it would have no change in behavior of this. If I were to heat this magnet up and get it really, really hot, I would destroy the magnetic field in this magnet, in which case it wouldn't matter how cold the copper is. This would just fall down to the piece of copper as if it was falling on the wooden table. So yeah, that was a good question. Good question.
So now we're up to some waves.
Bye.
We're not going away yet. There you go.
I'll get back to the microphone setting here. If one of you could take this off the table. Okay, so what I have here is what we call a Rubens tube. It's basically a flame tube where we can control the gas input, and hopefully we'll get high flames out of this. And then
Got it?
adjust it down to about there. So now we have just a whole series of little candle-like flames here. What we're going to do is, can you just hit me like number 3 or number 4 there on my light settings? Yeah, like that. Not too much. I want to have this dark and that light. I've got to, well, I've got to be able to see my meter. That's too much. 2 or 3, 4. All right, there you are, right there. Okay, so now what we have is, if I hit this with 400 hertz, you can see I have a wave front here, goes down, wave, comes down, wave, comes down, wave, comes down. Okay. I can change the resonant frequencies of this tube if I go up to another frequency. Somewhere around in here. There we are. So now we have 1, 2, 3, 4, and a 5 node there. Okay. If I, or 4, if I go up another 100 hertz, there we have 1, 2, 3, 4, 5. There we are. So now we have 1, 2, 3, 4, 5, 6. So 3 complete waves down through this tube. And here we go. We can turn this down a little bit more. So now you can see 1, 2, 3, 4, 5, 6, 7 waves. So 3.5 waves. And then the last one we'll do should be up here. Right here. So now we should have 1, 2, 3, 4, 5, 6, 7, 8, 4 complete waves that are traveling down through this tube from this frequency that we're at right now. Hopefully everybody was not too annoyed with the sound that is associated with this demonstration. All right, very good. Any questions on that? My learned team of colleagues can answer anything you have to throw at them. There you go.
There was a question in the chat, can you play music?
You can, but it doesn't show the patterns as nicely. It's just a lot of times what's happening is the flames come up real high and go back down and then pulse music of the bass drum, stuff like that. So you can get nice dancing movements of the flames, but you won't see the wave pattern. So now we're going to move on to some spectra. And for that, we have to put a diffraction grating over the front of our one iPad, our one camera. And I have to plug this table in too. I have the mic on me, yes. That is a good question. But here we have some sources. And I'm actually going to start on, oh, good. Thank you, Dale. Good deal. Right there. Do we also have it on that one too? Let's hopefully they're aligned in the right manner. I think that's a little crooked. Let's find out. So the first thing I'm going to use is this gas source right here. And oh boy. Let's see what our camera people are telling us. Do we actually see a pretty nice pattern on the screen that you have? Should we turn the lights down otherwise?
Lights down.
Lights down it is. There you go. So, you know, we're just doing this recording with iPads, and you can see that you can actually teach some spectra with a nice diffraction grating, putting it over the lens of your iPad or your phone, right? It doesn't really matter, about the same kind of camera, and looking at a source. And here we have what? Well, no, is that not? Is that neon right there? That's neon right there. There's a whole bunch of lines right there, isn't there? Aren't there? That's pretty, isn't it? But that one color we see without the diffraction grating, well, all those colors you see are making up what we see right there. And actually, that's the fingerprint of neon. When you're using a diffraction grating and sources, you're actually, you know, finding out the fingerprint of each individual element. And that's a beautiful thing right there. Can you see the second order?
Yeah. There you go.
There it is. Look at that. Isn't that nice? Nicely done, Daniel. Okay, so now we're going to move on to the second one we have here. And that would be what? Oh, let's see. That's an interesting color. but I would say that's mercury. And when you see those colors, you see it's not as many of those slices of light like we had before with the neon, but we can actually tell using the diffraction grating, using this kind of idea, exactly what this element is, because that's the fingerprint of mercury. And if we use this on one of those CFL bulbs, the old style CFL bulbs that, you know, we're trying to get rid of and move to LEDs, well, you know, we actually see partly these lines because there is a little bit of mercury in all those CFL bulbs. And we know that in this very way. So you're actually doing a little detective work, right? It's a fingerprint. So there you go. So let's turn this one off and move on to this one right here. Oh, and that's a nice bright yellow, isn't it? And this right here, ladies, gentlemen, this actually right here is something we have as something we saw in the sun first. This is helium. And that specific yellow color, well, we actually named helium after Helios because it's the sun, and that's the first place we actually saw that element. And then we said, hey, let's find that here on Earth. Let's see where we can find it. Let's see what it does. And that's when we found out all about helium. And now we knew, you know, we could find it here on Earth. And then we played with it in all kinds of ways, including Mickey Mouse voices and stuff. But it's actually quite precious. You know, as that helium leaves our Earth, leaves the underground places that we find it, it just floats up to the top of our atmosphere and actually floats away. Earth's gravity is not strong enough to hold helium to the Earth. It's quite valuable. And let's not waste it. Let's try to hold on to a little bit so we can use it in all those science experiments, because there are plenty we use with it. Turn that one off and this one on. And that right there is the most plentiful element we have in our universe. That's hydrogen. And you know, this is the famous Balmer series. This is the one we first really went after when we kind of figured out, hey, we can actually do this. And a lot of the ideas about quantum physics and these colors, these specific colors, that's where a lot of this started. So this is a beautiful way of seeing what these elements, the fingerprint of each of these elements.
So turn them all on.
Turn them all on.
The younger one.
Oh, colors, it's color time. There you go. And that's fun stuff. So there you go. That's beautiful. Excellent. And of course, you can do regular light bulbs, single filament light bulbs. You can even do some absorption with a neodymium bulb that actually absorbs a little bit. And if you use some of those LEDs that do lots of colors, they'll show a lot of pretty things too for your demo shows, or for anybody who just likes, hey, color, why not? It's a lot of fun. Lights, please. Let's see, I got it. Thank you. Yep. Excellent, excellent. Here, grab it. Give that to Paul.
All right, we got the dominoes next. I know you've probably all played with dominoes at some point. I have a unique set of dominoes that I built. Every domino gets larger by a factor of 1.5. So the double 12 is the biggest one here. It is made up of a sheet and a half of 3/4 inch OSB plywood. It weighs 100 pounds or more. Coming down, the tiniest domino is the double 0. Can you see that? You have to get really close to see that. So no markings on that one. That's the double 0. So this is 1.5 to the 0th power. So the height of this is 1. And then the next one is the double 1, and that's 1.5 to the 1st power, going up to 1.5 to the 12th power, all the way to the big one. You can see I didn't have a double 11, so we're going to use this double 11.5 instead. My wife doesn't think that's funny. I thought that was funny. I made this just for that joke. These guys are interchanged, so tells you what sort of group this is. All right, so the little ones we have to set up with tweezers here. They're a little finicky, so that's the double 3. And the double 2. All right. The double 1. This is the one that if I let kids play with, the double 1 and the double 0 seem to walk off, or I don't know, they get stuck in somebody's shoes. And I lose them. All right, and the double 0. It's a problem with live demos. There, that's going to stand up. All right, so big issue these days. The problem with the pandemic is they say the coronavirus had an R value of 2. That means that everybody who gets it, on average, passes it on to 2 people. Maybe somebody passes it on to no one, but then the next person passes it on to 4 people. This has an R value of 1.5, and you can see after 12 generations that gets quite large, and that gets huge. So it's important to keep that low, and there's concern that the Delta variant has an R value of 5, and you can see how much faster that could increase if that's true. So get your vaccine. All right, ready for the countdown? Sometimes they don't always fall, but you got to give physics a chance here. Ready? 3, 2, 1. Wow. All right, first try. Thanks a lot. Who's next, guys?
You want the broom to sweep those up?
We lose the little ones here. You need the mic here, Dave.
Oh, I do need the microphone. Okay, very good. So I have here a broom. We often take a broom and we show that we can balance a broom. That's not what we're going to use it for. We have here 3 glasses filled with water. They're moving away from me. On top of it is a plate of plastic, hopefully not glass. We have 3 tubes. We have 3 eggs. Right now, according to Newton's laws, they're just going to sit there for a very long time. Maybe millions, billions of years, no, but they're going to sit there for a while. They have inertia of rest. Now, what would happen if something comes in, a force is applied to these? Would we want to have it come in very fast or slow? We could move the cart around slowly, nothing happens. But what if we have a quick force come in? Well, that's what the broom is for. The broom is going to work as a spring. I'm going to stand on the broom. I'm going to stand on it. I'm going to line this up just right. Here we go. I'm going to pull back on the broom. I'm going to release it. 3, 2, 1. Ta-da! We have 3 eggs. Yeah, there we go. Very good. 3 eggs. We're having eggs in the morning. All right. Thank you, guys. You can have it.
Thank you. Well done. Give that to Sam.
Okay, let's make things cold again. Over here, I have a couple of pieces of a material that was discovered mid-80s, yttrium barium copper oxide. It's a superconductor, but at room temperature, it just behaves like a normal metal. What I have here is a circular track of magnets, okay? Magnets, normal metal. Kind of what we were doing over there, right? Except I had normal metal on the bottom, magnet on top. So normal metal here, magnet on top, and there's nothing exciting happening here. What's really neat though is if you take this material and cool it down, which is what I'm doing over here, I have bigger versions of this cooling down in liquid nitrogen. This material turns into what's called a superconductor. It's not just a really good conductor. A superconductor is something entirely different, better than just a really good metal. And now that this is in its superconducting state, it repels magnetic fields even if you don't move them. So you can see this thing is just floating. It's not moving. It's repelling the magnetic field, but it does something else that's really cool. If I give this a push, it's going to follow along with the magnetic field. So this thing is just following the magnetic field around the track. So the magnetic field lines that are stuck inside of this right now don't want to move around. And so this is able to follow this track around. So that's really cool. It's very different than a metal, a very cold metal that's a very good conductor near a magnet. It's very different. And I'm going to show you just how much more different this can be. So here's an array of magnets. And again, this is going to be not too much different, except once I squish that down, you can see it's floating, but I can flip this upside down. And the magnetic field lines stay locked inside that superconductor. So this is not a symmetric field. When the thing was flowing around this track, because it's symmetric all the way around, it doesn't look like the magnetic field is changing. Here, the magnetic field is north, south, north, south, north, south, north, south. It's a very confusing sort of magnetic field. So it looks different if I try to move it, and it stays locked. This now is north in the middle, south on the outside. Very symmetric. I'm going to pop that in there. Here, you get those hemostats off. Thank you. So you can see that this is free to rotate, and it doesn't even have to be centered on this thing of magnets. It rotates off center, and it also will spin around upside down, and it will spin around in that direction. And this does not happen with normal metals. So this is a quantum mechanical effect, which is, sure, do that one again.
Explain my Dale, press that in.
We have a question in the chat if we're actually handling something at liquid nitrogen temperatures.
Yeah, so as long as I do that very quickly, then I don't transfer enough thermal energy out of my hand to let my hand cool down. And but I certainly wouldn't want to hang on to this for any lengthy amount of time. I would get frostbite. So that's a very good question.
The other thing that helps us out here is these are encased in very non-thermally conductive plastic. So even though it's cold on the styrofoam that's in the middle, that's soaking up some of the liquid nitrogen, the plastic does not convey that heat very fast. So when you pick it up, you have maybe 30 seconds before any real damage starts.
Let's stop that guy for a second. There's my hemostats getting stuck to the magnets. And come on, get lower, get a little higher. You can go that way, you can go that way. Good enough.
A question in the chat, can you turn the track upside down?
The answer is yes, but I'm not going to do it. It's pretty heavy. But yes, I could turn this track upside down. This would hang suspended from the track and go around in circles. Yeah, but I'm not going to do it.
That's why you use the small separate piece.
Yeah.
So, you're right, exactly. That's why I did it with this one. So, but this would behave identical to this, just suspended.
Another question is, can you spin two superconductors at once?
Oh, on this at the same time? Sure we can. Stop.
Go.
You go. You go. What I tried to do with the little one was go underneath it. Nope. Caught it. Come on. You go down. You stay there. Okay, you go that way. Ah. Oh. This one's warming up. This one's old, isn't it? Yeah. So this one is losing its superconductivity fairly quickly. It's warming up much too fast. So has your oh.
I have a question, where do you get the pucks?
The pucks are made by a company in Israel. So we order them, and about a month and a half later, they make it through customs and into the United States. I haven't had to order any during the pandemic, so who knows how long that would take right now.
What's the name of the company?
The company is called Quantum Levitation.
Bosick already put it in the chat.
Bosick already put it in the chat. They are a frequent supporter of AAPT. They've been at the vendors area during our national meetings. So, thank you, Quantum Levitation, for supporting AAPT and our endeavors.
There's a question, what happens if you spin the puck on the track?
Yeah, so spinning does not work because the spinning motion is not a symmetric motion, right? Remember, north, south, north, south. If I turn the puck, the part of the puck that saw north and south is no longer seeing north and south in the same location. So it will not spin. No, I could spin it and leave it, but it will not freely spin on this track. Just like it would not spin on this set of magnets, but it does spin on that symmetric where the spinning looks the same no matter what angle it spins through. Okay, let's move on.
All right, we're gonna do something really dangerous. You need the mic.
One of you can get my foot to it. I'm a little.
Okay, so we're talking about magnetic features and things like we have here. So this pretty much everybody should recognize as, you know, your basic vegetable chopper. And as a vegetable chopper, we actually can chop some vegetables with this. Okay, and you know, if that's not good enough, we can chop them again. So this is your basic vegetable chopper. But what we have, the whole point of this is that this is a copper plate. And you have seen that if we put a magnetic field around the copper or a big magnet on the copper plate, we get an effect that can be seen and measured, okay? Well, up here, if I do this again and slowly, if you look at the top, when I release this copper plate, you can see that it takes a while before it starts to really move, okay? And that is because these two plates up here are magnets. Now, you know, if you get a professor that, you know, is really excited about stuff and he's forgetting what he's doing and he's playing around here and, you know, he might forget where his fingers are, right? Well, if they're down here, this is a bad thing because, you know, if he forgets where the magnets are, he's just lost 4 fingers, okay? So we try to make sure, very, very sure that the professors that we give this to really know what they're doing. But if you know anything about electricity and magnetism, you know that if I move the magnets from up there, where it's slowed down the plate, to down here, what's going to happen is that when I drop the plates, they should drop and slow down here enough that nothing happens, okay? They're almost at a dead stop by the time they get through here, which means that now any absent-minded professor is safe as far as how this drops through, okay? So you have to remember the people that you're giving this thing to. But it's all about electromagnetic induction and Lenz's law and eddy currents. When you drop this and let it go from a very small height, you can see that it takes a long time to drop past those magnets before it hits the bottom of the device here. All right.
Ooh. Did anybody know that David Sturm is actually an excellent musician?
I think I knew that. Let's see if we can get this going. I think one of the things that people have really found over the last 15 years is the Big Bang Theory has convinced you that physics is really interesting. And I think we all know that Sheldon at some point has a theremin to play with. And this is an actual theremin. Let's see if we can turn up the volume. I think the volume is down a little bit. Whoa, there we go. So what can we play here? What are we doing here? We're adjusting the frequency. Normally on a musical instrument, you open and close different numbers of holes. But here, as we get closer to the antenna, our spaceship takes off. I don't know. But we see how it goes lower as we get farther away. Now, the other hand's only controlling volume. Thank you, Sam. Oh, you turned me off there. Oh, very good. But you don't have to be on one side. You often see people doing it that way, but it works from behind. It works from the side. It works from the front. As a matter of fact, it works all the way around. It's an antenna. It's a cylinder. How many of you remember when we had rabbit ears and you would touch the rabbit ears and you would get a better signal, right? The same kind of thing's going on here. When I touch this, I get the highest frequency. Wow, that's really high. Oh, no. I think we're fading away to the next demonstration.
I'll play a song.
Oh, you want to play a song? Let's see. That's going to be hard to do on this. Okay, I don't think it's Beethoven. It's definitely not gonna be musical. This is just to play theremin. Give me a piano, give me a bassoon, give me a clarinet or a trumpet. All right, very good. Excellent. Enough playing. What do we have next? What do we have next? Well, I don't know. I think I only got one less.
Well, like our show, this is actually kind of a chaotic motion. You've seen these things behind as we've been going through, and I've been playing with them a little bit just to get your appetite whetted for what we have right here. So there are examples of chaos pendulums that people know of, and you can actually buy them from Amazon and things like that, smaller versions of chaos pendulums. And Paul Nord has kindly brought his little chaos inventions right here, just with really good bearings. And I think this can be printed off a 3D printer too. Yeah. And if you haven't been to Paul Nord's YouTube channel and subscribed yet, you should be doing that, because that gentleman right there is one of the most inventive people I know. And really, it's fascinating to see all the different ideas he has. He's really an expert also in the slow motion area of physics and other science. And it's fascinating to see what he puts up on his channel. So I advise you to do that. But these are beautiful devices. And if you actually email him, contact him, he'll actually send you the plans for those little chaos pendulums right there. Just like that, okay? So do that. But here we have an example of a chaos pendulum. And you know, a chaos pendulum, it's really kind of an example of when you take two different energies and they're kind of coupling in a way that's random. So the energy of this kind of motion here with this kind of motion here, well, if you put those two motions together, those two energies, well, they combine in a very, what we call, chaotic way. And that motion is hard to predict, right? We don't really know what that pendulum there is going to do next. It could do all kinds of things. All the energy can go into the swinging this way, or all the energy can go into that one arm there. That's what the whole idea is. And, you know, in life, we have a very good example of this. If you know the weather is actually a very good example of how energies combine in a very random way. So when you get the weather, they actually give you the weather forecast in what? In a percentages. They say, well, there's an 80% chance of rain, or a 90% chance of snow, or, you know, 100% chance of sunlight. But are they ever really right? Well, that's what we learned from statistics. You're not always right, even when you say, hey, there's a 99% chance, because you got that little tail there. And understanding science and understanding statistics are actually one and the same. So try to do both, okay? That's how we really understand things in a lot of different ways in life right now, okay? Try to do that. So here we have our chaos pendulum. This is what we call a single rot chaos pendulum. And rot, it's R-O-T-T if you want to look it up. And the gentleman Rott, I believe it was a gentleman Rott who designed this, yeah. And he said, well, that's fun, but let me do another one. So he invented the double rot chaos pendulum. So it has a arm right here that swings, and the mass here is the same as the mass that we have in this arm here, but this swings in the middle and this swings at the top. So that actually is even a little more chaotic than the single rots chaos pendulum we have right there. Fascinating motion. It's hard to keep your eyes off it, right? You want to know what is it going to do next? Kind of like a thunderstorm. When's the lightning going to happen? What's that arm going to do? And that's one of the beauties of science. That's what we like. One of the reasons we like science so much. It's really fun to see what's going to happen next. And here we have something we call an alago pendulum and a chaos pendulum. And I actually first saw this in Switzerland a couple of years ago when I was visiting my buddy Urs out there in Switzerland. And you know what? I saw this on the wall and they were charging an awful lot of money for it. And I just didn't have the cash at the time. So I said, gee, you know what? I wonder if my machine shop could build this. And they actually did. And now I have the plans for this. So if you're interested, contact me. I'll send you the plans, but you're going to need someone pretty good to put this together for you. And my friends around the country actually almost have all tried to replicate this themselves, because this is just a beautiful example of chaotic motion. It's kind of hypnotizing to watch as the energy dances between that big loop of metal and that pendulum that we have right there, that physical pendulum that we have right there. It's a beautiful example of chaos. And I don't know, I understand why it was hung on the wall and cost a lot of money as almost a piece of scientific art. But you know, it's a beautiful example of what you can do in the classroom too, or in a demo show, just to get people's appetite whetted about the beauty of science. So that's kind of nice, right? And you might be wondering about this one right here. Well, this is actually not a chaotic pendulum. It really isn't. But what we have here is a moment of inertia wheel. And what we have here is just a nice big physical pendulum like that. And one of my professors came to me one day and he said, you know what, Dave, there's a physics problem where they have this pendulum that has a wheel like this and, you know, arm like this that moves. And what's the difference in the period if you lock this wheel in place like this? Okay, and you do that pendulum motion. Well, it's just a physical pendulum, right? Nothing's moving a wheel right now. But if you actually unlock that wheel and do that same motion, okay, like this, will the period be longer or shorter? That was the physics problem. And he said, do you have that? And I said, no, I don't have that. And I went and talked to two of my really, really smart students. And I said, this is what we need. And I challenged them to design it. And then I took it to my machine shop after they did a CAD design. And they said, oh, yeah, we can make this for you. And they did. And of course, it was made the week before COVID hit. So a lot of people haven't seen it yet. But and my students who built it can't even play with it, which is unfortunate. But it's a nice example of what you can find if you challenge your students to do something for you. So once again, let's compare those motions. You have your block. You'll see it's kind of hard to know exactly the difference, but we can kind of see what that's doing when we do that. Well, now there's a rotation there, and it's actually a little shorter period with the rotation. And I'm not going to go and explain that. You're going to have to do the problem. Hate to tell you. So there you go. That's a moment of inertia pendulum. But, you know, once in a while, you want to go big or go home. Dale's motto. And what we have right here is the pendulum we were using in that physics show before COVID hit and knocked us off the stage. This is a simple chaos pendulum in that it's only these double arm chaos pendulum. And if I just give it a little bit of a shake like that, well, it does what any pendulum you would expect to do. It just swings back and forth, you know, just like that. Little play on the bottom, but that's about it, right? That's all we have. But if I go ahead and give this pendulum lots and lots and lots of energy, well, what a beautiful example of chaos motion. That thing is just hard to keep your eyes off of. And the outside arm swings so fast when all the energy goes into the outside arm. It actually sounds like a helicopter. And I'll tell you what, this is dangerous because there's so much energy in that arm when it's swinging fast. I would not want to get hit by that. That would hurt, okay? Don't make that at home. Yeah, I doubt any of you could make that at home, but I'm really glad I have one, to tell you the truth. And we'll be back on the stage the weekend of Thanksgiving. So come see us play with a big, big chaos pendulum, just like this in the show, okay? I think we have that as the next demonstration.
All right, Dale, thanks for plugging that. Dale's show is off Broadway, so I don't know if he mentioned that. If you're in New York, go see him. You can just stare at those chaos pendulums and you watch it do a whole bunch of different things and you sort of figure out all the sorts of things it can do. And you do this for 5 or 10 minutes and then it does something completely different and it's just amazing. There are a lot of physics demonstrations that are just exciting and end with a bang. And I know it's the teacher's job to bring excitement to this, so I'm going to try to get you excited about this one. It demonstrates the thermoelectric effect. So when you put two dissimilar metals together, a current will flow between them, and that current increases when you increase the temperature difference between the metals. And that's actually the effect we use to measure a lot of very high temperatures. This is one of those, though. My excitement when I look at it, I just sort of stare and it's just kind of amazing. So can you see under here? there are two dissimilar metals in the gap here. This side has a fin that I'm going to heat. And then on the back side, we're going to run some cold water. Dale, can you pour some cold water for me and hold this while I do that? And there's a big turn. So when we get a difference of voltage across there, a current is going to flow through this. And this single turn of just heavy copper is going to conduct a lot of current. It's going to draw this up. So there's a steel magnet D. So the magnetic field goes through the whole magnet there. And that will hold that up, and that will be able to support actually quite a lot of weight. So if you want to keep that side cold, and I will start getting this side hot. And here's where I know I'm supposed to be conveying excitement, and I'm just too amazed by it myself. So nothing yet. Nope. Stuck a little bit. Come on. I'm going to have to recirculate our cold bucket here. Out there, it's stuck. So let's make sure, see if it can hold some weight. This is a, what do we got there, Dale? A kilogram? Not quite holding 2 pounds. Back there. Need a couple hands to do physics here. Now it's holding up 2 pounds. We dare try it with 4 pounds. Got another 100 kilogram weight here, or 100 gram weight here. All right, so there it's holding 2 kilograms for about 4 pounds. I'm gonna turn that off. And once that temperature difference goes away, that current will stop flowing, and you will get the magnet will release, and it'll drop that off. So, and here's long, slow, and contemplative. I hope you're all impressed. I think this is just a really amazing demo. It's just heat holding this on. It's fascinating. They're fascinated. Okay, tell us more. The thermoelectric effect was really exciting back when, okay, all right. This is a demo show. This is just the fun stuff, the history lesson.
Okay, let's do another hot demo.
All righty.
So I do cool demos or I do hot demos. So this is a space shuttle tile. And like Dave, my students design things. So my student designed this as well. There you go. So why do space shuttles have these weird tiles? As they come back to Earth, they have to dump their energy somewhere. So where does it get dumped? There's friction between the atmosphere of the space shuttle and the walls of, or the atmosphere around the space shuttle and the walls of the exterior walls of the space shuttle. That friction heats the walls of the space shuttle. Heats it so much that those walls can turn red hot. But I feel nothing on my fingers. And we all know the unfortunate occurrence when the exterior tiles of that space shuttle were damaged. Now, from this top, I would not touch that. That's scorching hot. I can feel the heat coming off of this just by holding my fingers up there. If I touch that, I'd get a very, very bad burn. But underneath, I feel absolutely nothing. It's really a remarkable material.
That is something. Even after the glow goes away, too, can you look at that in an IR camera and see?
Oh, you would see it.
Yeah, you'd see that it's red hot.
But to put your hand there, it's still hot.
It's still hot.
Yeah.
Very dangerous.
Actually, if we drip some water on there, I wouldn't be surprised if it boiled right away. See if it boils. Yeah, could you hear it sizzle? So that's still boiling the water that's being
You
dripped
fry
on
one
it.
of David Sturm's eggs on that.
It's hot right there, but it's not hot over there. It's just not conducting much heat down.
Yeah,
down
this is not
at
hot
all.
right here,
It's only hot where you heated it.
just where I heated it. So the thermal conductivity of that stuff is
Pretty amazing.
tiny.
We had a question in the chat about where you get these shuttle tiles without stealing them from NASA.
Yeah, so NASA is now offering many items up on surplus. And so many of us at the universities picked up some of those shuttle tiles when they first went on surplus. And so they're being scattered around the country and learning institutions, so on and so forth. So
If you're part of a various outreach group and stuff, you can still contact NASA. They still have some that are available. That they will give you, barring certain conditions that they have for that. But for mostly for demonstrations and for classroom activities, that's no problem. They will send you a couple if they have them available.
And can you remind our watchers to, if they have questions, to please put them in the chat.
please put questions in the chat if you are watching the video or watching the demo show and you have questions.
Please give Dale your microphone.
I will gladly give Dale my microphone.
Okay, so the last the demonstration we have second to last before we do the Big Bang is just to show you some meteorites. Many people know about meteorites, have seen maybe small meteorites, but most people don't have an opportunity to see some large meteorites. At our university, we were fortunate that around 1900, we had one of the leading scientists on meteorite identification. So he got sent meteorites from all over the country. Not only that, but in 1846 and 47, the day this university opened, there was a meteorite strike 15 miles north of us in Homestead. And so a bunch of those meteorites are sitting, we have one here, we have a meteorite sitting over in the old Capitol Museum, and there's several others scattered around the state from that Homestead meteorite strike. So what they are is we have several here, and we have, this is a Homestead one. It's a chondritic, mostly chondritic, which means that it has a lot of rocky type substances. If you were to take a rock and break it open, that's what it would look like on the inside of this, except for it does have enough magnetic materials to be slightly magnetic, okay? This is what it looks like, and if Daniel can, if I can get this close enough, this is kind of what it looks like if it's broken open. It looks like just a regular rock that has been broken, and you know, if you had some iron filings or something in there, that's basically what it looked like. And this one also is slightly magnetic, but we call this, is classified as a chondritic meteorite. On the other hand, we have a meteorite here that weighs about 10 pounds. This is one of the fragments from the Diablo Canyon meteorite strike in Arizona. And it is highly magnetic because, as you can see on this one, there are no rocky pieces in it. This is all nickel iron construction or composite. And this one is highly magnetic in its construction. So there are different kinds of meteorites, different sizes of meteorites. Many people have seen small meteorite fragments, but these are some that we are fortunate enough to have because of the fact that we had a professor who was one of the leading identifiers of meteorites in the world. All right.
What do we learn by looking at meteorites?
So we learned many things. You can see I have a couple here that have been sliced open. So they were looking at metal composition, which is why we know that it's nickel iron. You can see that this one has had its tip sliced off, so that they were looking at what was the composition of this inner core that you see here. And you can see that there was a little chondritic portion of the meteorite here that didn't get burned off completely when it came through the atmosphere. But you're looking at composition. You're looking at what is the thing composed of, because now we know that several of the meteorites that were picked up at the North Pole in the Arctic came from Mars because they have the signature. If we look at Mars and we can look at Mars with a spectroscope when it's glowing, we can figure out what, just like the fingerprints of the elements that we were looking at with the glasses or the gratings, we can figure out what Mars is composed of. And we know by looking at those meteorites, what their composition is exactly the same as Mars. And curiously enough, it appears that a couple of those Mars meteorites had what looked like primitive life forms embedded in them as fossils in those meteorites. So we can get a lot of information from what we see as the composition of the meteorites. Do they come from the asteroid belt? Do they come from maybe a strike on Mars that ejected some material and then made its way to Earth as a meteorite? And so there's a lot of stuff about the solar system we learn from meteorites that we gather and analyze.
Why do we see the meteorites glow like we see when they're coming through the atmosphere?
So that is just frictional heating, the same as when the space shuttle comes through the atmosphere and the tiles glow because of the frictional heating of the atmosphere on the object. It's the same thing here, which is why many of the big meteorites do not survive intact. They get partially through the atmosphere and then they start breaking up because the heat stresses are so much that it breaks the whole meteorite apart as it comes through the atmosphere. And then there are many pieces that if they survive, hit the ground. And that's where we get some of these because this is just a portion of the total meteorite that hit. This is just a portion of the total meteorite that hit. And that's the case for many, many of the meteorites. They break up before they hit the ground.
Fantastic. Thank you, Dale.
All right.
May I borrow your microphone?
You may.
I think we're just about there. We have about 5 minutes left before our end time, and we like to end on time because we respect your time. We know that if that's important, just like our time's important. So we're going to end with a chestnut of a demonstration that I first saw about 25 years ago, and some people have it and some people don't. And Dale, would you please back that table up and back up yourself a little bit? I just want to be careful about this. And what I have right here, well, what's interesting is, you know, way back when, people who worked in, let's say, an office were known as pencil pushers. That's right, they were known as pencil pushers. And why were they known as pencil pushers? Because they spent their whole day writing facts and figures down like this. And that meant they were pushing a pencil down on a piece of paper. And they did this all day long. And that's what I wanted to avoid when I first got out of college. I didn't want to be a pencil pusher. But you know, I wound up being one anyway, because what I have right here is a device that can actually push a pencil. And I owe making this device to a gentleman named Dr. Richard Berg from the University of Maryland. Just a shout out to him because he was a wonderful gentleman at the university and really introduced me to a lot of fantastic demonstrations. But what I have attached to this tube right here is a fire extinguisher. And I'm going to ask Sam to step back because I just want to show you that when I press this, it shoots a stream of CO2 through this tube. So if I take a pencil and I put it inside the tube, push it all the way down, and then take some board, put it right here, tighten it into a really strong vise, just like that. That's tightly in there. And Dale here, he's going to help me pick up my shield because, hey, you know, demonstrations can be dangerous. And we don't want any danger in doing our demonstration. So if you'd like to live for tomorrow. So we now have those two boards right there. And I have a pencil at the end of the tube. And I'm now going to go ahead and take that same CO2 you just saw come out of the end. I'm going to do that again. But what's inside the tube now? A pencil. We're going to be pencil pushers. So we're going to do some force. We're going to shoot this pencil. Oh my goodness. What have we done? Well, that pencil has basically penetrated those two pieces of board just like that. So even though I wound up being a pencil pusher, I have a lot more fun than your average pencil pusher. But I think someone's going to give me a hand now. But first, we're going to put a pencil inside because a lot of the questions I get from people when I do, let's say, the ping pong gun or some kind of projectile, pusher, what happens if the goes into your hand? We've never done this. Dale just happened to have a mannequin hand at hand. No pun intended. Well, maybe it was, I don't know.
Move it up a little if you can.
How's that? So now we have a hand in there. And once again, Dale's going to give me a hand. Thank you, Dale. So now, hey, we're all scientists, right? Any human being is a scientist. It just means you wonder about our world, our universe. And what we're going to wonder about is what happens when I push this pencil one more time? What will happen to our hand? I say we do the experiment and find out. Oh my goodness. And that's the first time that demonstration has ever been done. And there you go. Hey, a big round of applause for all these people right here. Come on up, everyone. That's for you to say goodbye with, because you're the host.
Yes. So from the University of Iowa, Paul Nord, myself, Dale Stille, David Sturm, David Maiullo, Cliff Bettis, and Sam Sampere over at the end, we all say goodbye and good luck and have fun. And don't do these at home.
Thanks for joining us. Yes, thank you for joining us. I hope you enjoyed our show.
Don't try
Good night, all.
Are there any questions in the chat while you're there?
Everyone set up the seat back.
We got a lot of thank yous. Thank you for the fun time. Perfect. All we're going to do is get all this up on the table somewhere. If you have a question, we'll sort it out to you. David, we have a question. Will the recording be available to us?
Right, I've typed that up. We don't control the recording. It's through AAPT programs and conferences. So through the usual AAPT resources, we'll wait to hear from them if the recording, how and when it will be available. We especially want to thank all of you for being here tonight. It's good to see so many people from around the world, guys. We've had people from the Philippines, Nigeria, China. So this has been great. One of our goals with the Physics Instructional Resource Association, our group of people who love doing demonstrations and helping advance the teaching of physics, is that we are worldwide. And so thank you again. I'm looking here to see if we have any more questions. We do have a few more.
Thank you from Australia.
Australia, Jordan, Argentina. Wonderful, wonderful. I have sent a link in here you can follow. We're just beginning to work on our website, and you can follow us and peek in on us once in a while. If you go to this website, you'll see some links to a website at the University of Colorado, and a really important link to the website here at the University of Iowa, who has so wonderfully hosted us here. The work of Dale Stille is incomparable. He has accumulated everything one could possibly need to teach physics. So we are very glad to be able to share these things with you tonight from here. Dale, you have a lot of people who are shouting out to you from the Iowa community, past students. I'm so glad so many of you were able to hear science ed grads from the early 90s and other past graduates. We see the impact that we can all have by sharing. The 7 of us have all come together from 7 universities where we all do similar things. And, every university department hopefully has someone like us out there doing these sorts of things. Let's see, past students of Dave out there. That's very good. Sam, you've got a lot of people here that have come in for you. That's great. Excellent, excellent. Well, if anyone has any more questions, I'll keep this live and check back in once in a while. We are going to go ahead and stop the recording. So thank you all for being here today.